So we'll begin talking about unconstrained problems that are nonlinear. Of course, linear, if it's linear and unconstrained, that's kind of a trivial solution. So we're looking at nonlinear problems here. And so we'll just have some function that we've shown here. And again, we're just looking at one independent variable here to demonstrate the process. But of course, this one has a lot of peaks and valleys, and of course, wherever there's a peak or valley, as you learned in calculus, that slope is equal to 0, and those are local max and local min points. And so when we're doing optimization, that's usually what we're trying to find, right? We're trying to minimize or maximize something. And again, there is the case of an inflection point as well. So, simple equation here, quadratic equation. What if we're trying to find the minimum value of y? Well, we could take the slope of that and set it, the derivative, the slope, and set that equal to 0. So in this case, y prime is 4x plus 8. And if we set that equal to 0, of course, there's only one value for which that's true, and that's x equals -2. And so we conclude that that's either a maximum or a minimum. And looking at a graph, we certainly can confirm that we hit a minimum value at x equals -2. Now, of course, analytically, if we want to know whether that's a max or min, we have to take the second derivative. And if that second derivative is less than 0, then we have a maximum value. The second derivative is greater than 0, that's a minimum value. And if the second derivative is exactly 0, that means it's an inflection point. So in this case, our second derivative is positive 4. And so we know that that is a minimum value of the function. Okay. Now here's one that's a third order equation. We're trying to minimize it. And again, we take the derivative of that if we're trying to do this analytically and set it equal to 0. And we get a quadratic equation. Using the quadratic formula, we come up with two solutions there. So x equals 1 and x equals 1/3 are points where the slope is equal to 0. And again, looking at a graph of that, we can see one of them is a local max and one of them is a local min. But you do notice that if we go way below 0 or we go way above the 1.5 that are shown here, this is going to keep going negative, this one's going to keep going positive. So these are not absolute max and mins, and you can see that by the chart here. Even within this range, these are local maxes and local mins. And so always got to keep that in mind when we're doing optimization of nonlinear problems, is that often we're going to find a local max and a local min. So we're not sure that we have the absolute maximum and minimum values. So again, you're getting local extremes, so you have to make sure when you're interpreting these results that you are finding what you're looking for. Now, MATLAB and Excel have some tools here. In MATLAB, there's a function called fminsearch, so not too different from fmin0 that we looked at for root finding. And we can still do those with Excel Solver as well. Now, in either case, if there's more than one local max or local min to be found, then our guess value is going to determine which one of those we come up with if there's multiple solutions. And if it was a pretty simple problem, I'd much rather use Excel, since in MATLAB you have to write and save a separate function to be able to run fminsearch. But we'll show an example with that anyway. So going back to this simple example that we looked at, example 1, if I want to use fminsearch, first of all I have to write this as a function. So we've written a lot of functions now. First word, function, lowercase. Then what is the output is y equals name of the function, followed by, in parentheses, the argument of the function, which in this case is x, and there is our equation for y. So from the MATLAB command line, what we would run would be fminsearch, and in parentheses, the arguments of that function would be the function name, beginning with the and sign for that, and then a guess value. So we just arbitrarily chose 10 as the guess value, and you see what our answer is, -2, which we found earlier. Now, if you assign that answer for that function to be a 2-by-1 array, you get both the x and y values of that. So in other words, notice I'm assigning to the fminsearch command, which is the same as it was last time, but now I'm assigning both x and y min. And what comes out of that is the value at x that minimizes the function and the value of the function at that minimum value. And again, you can see that that is the solution, x equals -2, and y is equal to -14 at that point. Doing the same thing with Excel Solver. Again, put in a guess value in x, and in y we put in the equation. And instead of using goal seek, which just lets you, it would let us make a specific value for y, Solver, in addition to doing setting things to a specific value, can also find max or min. And so we want to minimize our objective function, which is in cell C4, the y value, minimize it by changing the x value. And again, there's no constraints on this problem, so you just click solve. Oh yeah, one other thing too though is that there's a box that says make unconstrained variables non-negative. You want to uncheck that to make sure that we can allow for negative values of x to show up. And if we do that and click solve, we get the same answer, -2 and -14. Okay, so that's a simple example of doing nonlinear unconstrained problems. But most engineering problems do have constraints. So in the next video, we'll start with linear problems where the objective function and all the constraints are linear, and work a couple of examples of that.